Professor.
Hi again, Camilo and Marcella and everybody else who is going to join us later on. And for those who are going to watch this one recording later on, hopefully it's going to be available for them as soon as possible, because that relies on Zoom when it makes these things available for us. So today we're in lab 2 basically, and this lab deals with capacitance, capacitors. So if you're not familiar with the process basically by now, you really should get yourself familiar with it. Let me go back quickly in here and find first of all where the lab instruction is, and then share with you the screen so that you understand how this class is graded. Share lab 2. Again, this is out of 171 points. So if you're wondering how is it going to get 171 points, easy. All you have to do is look at the rubric, which is really going to be your guidelines on what you need to do. Okay, every single point in here on how this is graded, it's in here. So your name or names is graded. Objective is very important. I'm going to talk about the objective now because I think we need to get this thing mastered. Answering the questions, doing the activities and doing the measurements. Okay, each measurement is worth 1 point. Then filling the table, every cell is worth 1 point. You have 80 cells, 80 points. And then graphing, in which case either you do it on PDF or you do it outside of PDF, like using Excel or whatever format you like to use. It's up to you, okay? But the graph needs to have proper scale, x-axis, properly labeled also with the y-axis, data points. If you have 20 points, you need to represent those points on the table. So don't draw basically the trend line. And the trend line, when applicable, when you're asked to do, for example, slopes and things like that, in this lab you will. So all of this is worth 6 points if you do everything correctly. If stuff is missing, you get these things, and then you get more questions, another graph, more questions, another graph, and another table. Again, table in here has 9 cells apparently. Then another graph, more questions, more measurements. Each measurement is worth 1 point, more questions, and again, more measurements, more questions, and more data points, data measurements, that is, more questions, more data measurements, and then the final question before the conclusion. Conclusion needs to tie into your objective. So let's look at this lab report. Stop sharing, and let me share with you the actual lab report, okay? I hope that you guys are looking at what says lab 2 in here, which is a PDF file.
Yeah, it's on that screen. It says lab 2.
Anyway, the point being in here is the point of this lab report forms is not constrictive, constraining, okay? You can choose whatever format you like. You don't need to use this one. As a matter of fact, if it's does not suit your needs, in a sense, the lab report is asking for something and you cannot do it on this lab report form because it's deficient. It does not have enough space, or probably there is no room for what to write the answer. Then in this case, it becomes your responsibility to answer that question or provide that item that is required for the grading. So it is important to know that this is not supposed to be a replacement for what you're supposed to do. So if you cannot find where to do this report, ignore it. As a matter of fact, if it does not work for you, you have to come up with your own version of it, either basically stating, okay, my name is so-and-so, this is the objective of the lab, you write it, and then you go question by question. The only thing I ask is, because I go by the rubric when I'm grading this one, first of all, is to follow the order in which the rubric is going, because that's exactly what this lab report form is doing also. And a number of things, okay? Help me in your own report, okay? Whether you like to use this one or something else. Again, if you want to print this one and fill it by manually, which you can do too, please make sure you can read your own writing, because Sometimes it may be obvious to you, but somebody else might not be able to read what you're writing. So if you're going to choose to do that option, which is your prerogative in a sense that you can do that, then make sure your handwriting is clean and clear so that they can read it. Furthermore, when you scan the document, make sure also it's readable, because it may be perfect if you hand it in. But when you scan it, things start to look all kinds of fuzzy and not clear, and the picture is not really focused, and now I cannot tell what you're saying in there, okay? So this is in general for all lab reports, so whether or not for this one or another one. It is important that you put your name in here, and any person who worked with you, hopefully no more than 3 though, I mean, including you, that is no more than 2, and you, that is 3, okay? Please observe all the guidelines in terms of safety and health when it comes to gathering together. You can work together online anytime you wish, and working on this lab reports. This is a lab report. It is 25% of your overall grade. Which means it makes a big chunk of this class. It may be the difference between passing and not passing. It is for sure the difference between getting a B in this class or an A and not doing that. So lab reports are of extreme importance, so don't take them lightly. Furthermore, they are not exams in a sense that you don't have to work on these things by yourself. They're supposed to teach you something. You're supposed to learn from them things, including on how to do the lab report itself and do the activities and connect the concepts and so on and so forth. So take them super, super seriously, because they're only second to finals in terms of weights and things like that. So they're very, very important, okay? So the objective in here needs to be concise, no more than 1 paragraph. It cannot be 2 paragraphs or more. It has to be less, paragraph, basically 1 paragraph in which you state exactly what needs to be done, the main points of the lab. Don't go in detail and start talking about all the different activities in the lab, just what you're supposed to do in the lab. It's a good practice to come to it back at the end, because of the situation we are in right now in COVID. So sometimes it may not be clear what you're doing until you're done with it, until now you think about it. What did I do? This is what I did, this is what I did, this is what I'm supposed to have done, and so on and so forth. Then you can come in here and put it basically in perspective, that this is what the purpose of the lab is. Refrain from using the pronoun I. Oh no, I can't write with this thing in here. Can I write with something in here? Comments. I. Don't use I at all. Try not to use it, okay? Also, what is this thing in here? I, okay? Do not use the student. That is not appropriate at all. You can use we, or you can use the concept itself that is being explored. For example, today we're going to use capacitors. You can start with capacitors has been measured or has been measured, or the purpose is to measure the capacitance. So you can state things along these lines, but you don't say I will or I did. And this is true for throughout the entire lab, by the way, okay? No need to relate any numbers in here, anything that has to do with the background of what you're doing. It has to at least be 2 sentences. When I say 2 sentences, please do not write 2 sentences only, just because I said you need 2 sentences, because you probably need far more than that. And the other thing also, it has to be really targeting the topic. So from now on, I'm going to be picky about these things to see that you really are hitting on it, okay, are really on the topic. Now, this thing has a spell checker. If I come in here and start typing, you will see that this thing has a spell checker. So for example, why is this all black now? Oh, because I have stuff in there. So for example, this is not, I made a mistake in here, correct, because I made so many mistakes in here. You see here, it helps me. So keep at least, because this is what is known as a rich text environment. It helps you in a sense keep the structure clean. I need I don't grade for grammar. That's not what we teach in here, at least in physics. But the point being, your idea has to be clearly communicated. If it's vague and I have no idea what you're talking about, or it's not clearly what it needs to be, I will make a comment of it. You may lose points and you may lose a lot of points that way. So you really have to be precise, concise, and descriptive of what you're doing in there, which means that the English has to be proper in the sense to address those things. So this is basically the objective in this sense. There is a big connection between the objective and the conclusion, which is toward the end. The conclusion and the objective need to be connected somehow. In the conclusion, you need to refer somehow to the objective, okay? Because those two, the objective promises what you're supposed to be doing, and the conclusion is whether or not those promises have been fulfilled or there was issues in there, okay? The conclusion can go far beyond the objective. It must go far beyond the objective to discuss the results. The results also, you need to refer to data in it. So we're science, so we communicate with numbers. So you have to refer to results with data and errors, because you will see errors everywhere. So now, you don't have to list every single result in there, but the main points, especially the ones addressed in the objective, okay? An overall error. Let's say, for example, you ended up with an error in one place of 2%, an error 1% in here, an error 0.7% in here, an error of 1.3% in here. So it's overall between 1 and 2% the errors. However, there was an error, for example, of 12% or 11% or even 8%. That stands out. In my conclusion, I need to address that. I need to talk about, for the most part, the errors for this and this were this much. However, for this measurement, it was this high. Probably do, and now come up with what may be a reasonable explanation to you. You're going to be rewarded for the effort. You may be not completely on target because it's your theory, but again, based on what you think might have caused that error. Again, we're doing simulations in this case. For the most part, simulations may miss the target, but if you're careful enough, they should most of the time give you good errors. On real lab, you will have situations like that one, okay? So when you start thinking, was my measurement, was my device, the probe that I use, was it properly calibrated or not, okay? Maybe it was offset. So all of your averages were off in this case compared to what the theory is supposed to say. So in this case, the calibration may be a problem. Was it an issue of, for example, and that's a problem that you should fix yourself. That is your problem, actually. If you do that, usually scientists get punished for it a lot, okay? Is it something that has to do with the way that I was doing measurements? Maybe this one was measuring, for example, in amps, whereas the current was changing in milliamps. So I really should use a galvanometer instead of an ammeter to measure these currents of these small variations. I'm not seeing any variation. You're asking me to graph something that depends linearly, but I'm seeing a flat line. And again, in this case, there is a problem. If I do the error analysis in here, I'll find big mistakes. So in this case, that's probably what happened. So in this case, there is a choice, again, of the scale that was not correct. So there are all kinds of sources of errors. Sometimes the system itself, those are systematic errors that come from the machine itself. And you have no control of it. The machine will tell you, I can measure, for example, what is that meter stick that I had in here earlier? I was looking at it and then I lost it and then I found it and now I lost it again. Okay, if you look at the centimeter ruler, usually it has denomination in centimeter. But if you have a place that you want to measure, it's finer than that. So this one can measure as much as a centimeter. It cannot go any further. So that is a limitation from the measurement device. So that could happen too. Okay? So those are the things that basically need to be addressed somehow in the conclusion in connection to the objective. I hope that down the road, you're going to develop this skill. Physics is not about what we're doing in lecture. That is in part of it too, understanding how things are coming and coming up with theories and numbers and things like that. Physics is what we do actually in lab, because if you cannot measure it in lab, it's not physics, it's math. And we're not doing math in this class. Whoever says that we're doing math is wrong. The math that we're using in class, in a sense, it's like a fake thing, just to understand the real thing, which is this stuff. I hope that this is clear, okay? Good?
Yes, sounds good.
Good here.
Very good. Very good. Look.
Clear as crystal.
Yusuf, are you? Oh, okay. Okay, make sure you guys. Oh, I'm sorry. I thought you said it's good. Now, good. Thank you, man. Okay, so here is part of the background in the theory. We have Q is equal to CV. That's what we did in class. Basically, V is equal to Q over C. And they gave you now 100 microfarads, that's C, 15 volt, and you're supposed to find the charge in it. There is a question here, if you double the voltage, how much the charge is going to go? It's going to double. Please do not use yes or no, or just answer with numbers, okay? You need to have it in full sentence format. I would answer this question if it asks for me to show that I'm really not just filling any nonsense in there and last minute things in here. I say the following: for a capacitor of capacitance 100 microfarads and a voltage difference of 15 volt across it, the charge is, then I can do the math. Then I say Q is equal to 100 times 15, and it's what? 1,500 micro coulombs. Okay, that's fine. Then if I double the other one, because of this linear proportionality, the charge will double. So in a sense, it has to be full sentences, short answers, yes or no, or just numbers. They're no good. They show a lot of basically, you need to show and express your knowledge. You need to express it in a scientific fashion. I want you, when you finish this class, to be able to communicate your ideas clearly about what you learned from every single situation in physics, okay? So communication is an important skill in science and physics, and this is with purpose actually of the lab reports. So that is really one of the objectives of them, is to be able to communicate your scientific ideas in a scientific method to anybody else, okay, later on who approaches it. This is not a math homework, so that you just plug in the numbers in here, or a physics homework where you just Q is equal to 1,500 microjoules, which brings me to another point, coulombs, I'm sorry. Which brings me to another point. Anytime you miss unit in the final answer, you're gonna lose points, whether in a lab report or an exam or anywhere else. Because if you don't include units, you're not talking about nothing. You're talking about basically some abstract concept that has nothing to do with what we're doing, unless an object that does not have units, like an angle, for example, which is in radians, which is just a number, okay, or things of this nature, okay? Things that don't have units, it's fine. But things that, like, for example, a charge in here needs a unit, so you have to have a unit. If you forget that, you're going to lose points in these things in here. And if you go back to the rubric, you will see that the rubric talks a lot about the units. Okay. They gave you now a better value than the one that I gave you in homework problems and when we do class stuff and things like that. And exam, I will take what you, if you write it correctly, which is 1 over 4 pi times 9 times 10 to the power 9, inverted basically. 4 times pi times 9 times 10 to the power 9. You take the whole thing and you put it backward. That is epsilon naught. In any exam I do, or any problems I do, that is a number I go by. However, for this lab, this is a number we're going to use. This is closer to the actual number. This is epsilon naught. Obviously, it's a very small quantity, okay? And this is the expression for a parallel plate capacitor. That's what we found in class. And this is what the whole lab is, basically. We're going to be dealing with this parallel plate capacitors. So again, what is a capacitance? So a parallel plate capacitor with an area of 100 centimeters squared. So the area is 100 centimeters squared. And a plate separation of 0.1 millimeter or 100 micrometers. So D is 0.1 millimeter. And again, make sure you convert things to the metric system, because this guy is in farads per meter. This area must be in meters. It's in centimeters squared. The centimeter is 10 to the negative 2. So when you square it, it's 10 to the negative 4 meters. So you have to multiply this number by 10 to the negative 4. And this number has to be multiplied by 10 to the negative 3, because a millimeter is a thousands of meters. So don't forget this step. It's critical. Otherwise, you'll get some nonsense capacitance in here. Okay? So C, you're going to calculate it using this number for epsilon naught. And if you double the separation, how does the capacitance change? Again, if D doubles, the capacitance should shrink by a factor of half, or by a factor of 2, I should say. And you have to be precise in your language. Because if you shrink by a factor of half, that means you double. You know that. Okay? If you grow by a factor of 2, that means if you grow by a factor of what is it? By half, that means you go half or something like that. So you have to be careful with the length. Okay.
Professor, so for number 2, when we plug in our values, we're converting the 0.1 millimeters to meters so that it's in the same unit as the epsilon naught.
Everybody has to be an SI here. In whatever you're working in here, everybody has to be an SI. Distances are in meters, which means areas are in meters squared, not in centimeters squared. Okay. Volumes are in cubic meters, not in cubic centimeters squared or liters or any other unit for volume. So everything has to be in SI. Distances are in meters. Epsilon naught in farads per meter. Farad is not a fundamental unit, but it's a derived unit in the SI system, so it's good. Newton also is a derived unit in the SI system, not a fundamental one. The fundamental ones again are the meter, the kilogram, the second, and the ampere. It's not even that Coulomb stuff, okay? And we're going to discuss that immediately next Tuesday when we meet for chapter 25. That how Coulomb is related to the current, okay? The charge and the current, how are they related? So in other words, yes, absolutely. Everything has to be an SI, especially in lab stuff, okay? I mean, you may get away with it in a homework or in a problem and here and there, but in a lab, you have to be very careful unless you are using a different system, which is acceptable also, but not in this particular lab. So the other system is called CGS, centimeter for distances, grams for kilograms, for the mass, I'm sorry, grams, and for the time is seconds, and for the magnetic field, I think they use Ørsted or use Gauss or something else, which is not SI. They use Gauss, they don't use Tesla. So they use different unit system. But no, stick with this one. Don't. There are too many of them out there to get confused with things. Stick to SI because that's hopefully. Is that what you used in 4A, or did you use a different system? Do you remember? Anybody?
I don't remember.
Oh, that was probably number 1 item from chapter 1, I think, from physics 4A, which was dealt with the units. And the only unit that was missing there is the ampere because there was no electricity in that class. Yeah, that's the item. Okay, so stick to meter for distance, kilogram for masses, and second for time. Okay, nothing else. Okay, somebody else might be using the light year for distances, which is fine if you are using it somewhere else, but not in this class. Okay, convert a 0.1 millimeter to a light year. Oh man, how many light years in a 0.1 millimeter? That's going to be fun. Not this lab, okay? Don't do it with this lab, okay? Please, okay? Again, it has to be full sentence with proper units and everything else, okay? In the dielectric, this is the same expression. I know probably I used in the classroom epsilon R, which is a relative permittivity, but in textbooks and other places also, they use the letter kappa. The letter kappa in here stands for the relative permittivity. It's a number, it has no units. So every material has its own epsilon, which is different than epsilon naught by this factor kappa. For example, the vacuum exactly epsilon naught, because 1 times epsilon naught is epsilon naught. In air, which is almost epsilon, slightly higher than epsilon naught, okay? That's basically why we take the same value for air and vacuum. Now, for Teflon, it's 2.1. An interesting one is for paper in here, which is about 3.7. So this is typical numbers now that for the relative permittivity in your kappa. At some point in this lab, you're going to be dealing with that. You're going to have a dielectric in between the plates. So we're going to build this lab. You can actually do it at home. You're going to get an aluminum foil on one side, another aluminum foil on another side, and bring a piece of paper and put it in between them, okay? And now you have all of a sudden a capacitor. And if you're worried how much is the epsilon for paper, here it is. It's about 4. 4 times epsilon naught. So it's what is the number? 8.8 times 4. 10 to the negative. So it's about 30 something or 35 or something like that. Or 3.5 times 10 to the negative 11 farads per meter for your capacitor that you just made. The only thing is you have to know the width of this paper, And if you don't know the width of this paper, take 500 of them, which is just a ream of paper, and measure the width and divide by 500. Now you know. I mean, the depth, that's what I meant, not the width, not this distance. The depth, how wide, if you're going to put it between plates, this is basically what you have to worry about, how big this thing is. So what you do in here, take a ream of paper that has 500, measure it, and divide by 500. That is roughly how much the the paper is. So you can use that for your to have fun with at home. And you made in the lab, we used to make capacitors when we were in person, but now I'm hoping that you guys will develop that skill and become really handy with these things, okay? Because physics is not just about, like I said, it has nothing to do with math. Math is just a tool, no more, okay?
I'm gonna email the admissions and tell them you should mail me the stuff to make a capacitor.
No, you can make it yourself, Marcella. Now you have plenty of stuff in the kitchen, I'm sure, okay?
I don't think my mom would approve.
Come on, man.
She's gonna get very mad at me.
No, she wouldn't. No, she would just. Okay, at some point we're going to be building motors. Okay, so when we meet on the first midterm, I'm going to be sharing with you a bunch of stuff. Actually, I'm going to give you things to take with you home, namely magnets and also coils for making your coil. Basically, wires basically to make your coil. And also batteries and battery holders and stuff like that with the instructions on how to make them, basically. This is part of chapter 28 or 29 down the road after the spring break. You're going to make your own motor. You're going to take a video for anywhere between 5 to 10 minutes to explain how the motor works. Hopefully it works everything for you. And when we meet back again for the final, you're going to bring the materials back. We leave them for the lab, in the lab for the next semester and so on and so forth. Okay. So I clicked on that link. Let me stop sharing with you the screen and share with you this screen. So are you guys looking at the FET interactive simulation capacitor lab? Yes?
Yes.
Okay, this is actually an HTML file, okay? It will tell you if your browser is compatible with it or not. If it's not, then it's not gonna work for you. You can download the Java version of it, okay? You can work with the Java version for it. And for that also it requires a Java, not JavaScript, Java itself, which is a different kind of programming stuff. Anyway, so let's assume that your browser is compatible with it. So we're going to click on the simulation. And at some point it's going to load. And it loaded. Okay, finally. Once it loaded, in here you have the view and how you view things. For example, it's showing me the plate charges. Right now there are no charge in it because there is no voltage difference in here. This is the battery. It's sitting at 0 volt right now. So there is no voltage in here whatsoever. So I can't do anything with it. And I can see the electric field, and there is no electric field because there is no, you need sigma in here and you need negative sigma in here. There is no charge now, so there is nothing in there. The capacitance right now, it's telling me it's 0.89 times 10 to the power negative 13 farads. So it's 0.089 picofarad. So it's a very, very small capacitance right now. At some point, they ask you to change the area to something like 400, I think. This is the maximum you can do it, 400 apparently. And then to shrink the distance to 5 millimeters. So this is a big capacitance right now, 0.708 10 to the negative 13 farads, okay? So this is the capacitance. If I start putting charges on this one, I can put small amount of charge. How much voltage do I have in here right now? I don't know. So I need to bring a voltmeter in here. So here is my voltmeter. This is the COM port. Every voltmeter has a COM port in it, just like this one, okay? This is where the COM port goes. Sorry, it goes in here. And this is where the voltage goes, voltmeter in here goes. If I'm measuring the current, I have to switch it to the current location. Okay, and that becomes a current now. So this side is only for the current. This one is for everything else. Like this one is actually a multimeter, not a voltmeter. It measures, among other things, voltage, and it measures currents, and it measures also actually resistance in ohms. It measures also capacitors too. And let me see what else does this measure. No, this measure capacitance, or did I make up that thing there? Measures, yeah, it measures the capacitance too. And it measures also the frequency, it measures the temperature. This is actually a multimeter, a big multimeter. And believe it or not, it's about $20. So these things are not too expensive. Anyway, take this one, and usually you put it where the cathode is. This is where the cathode is, okay, of the battery. And this one goes to where the port is. So right now it's reading 0.238 volt. That's why you see charges in here, okay? That's why you see charges in here. I can increment this one slightly and you will see more charges in it. What that arrow was showing for you is the direction with which the electrons moves. The electron move in the opposite direction to where the current is, okay? You can disconnect the battery. What is this one in here? What is this? I've never seen this one. No, connect the battery. Never mind that, okay? Use the battery. Okay. So again, you can have more and more and more voltage all the way to 1.5 volts. So if you're curious trying to find the voltage, just bring a voltmeter like I did in here. If you don't like this picture in here with the electric field, just remove it. If you don't like to look at the charges now, remove them. And the voltage now is telling you everything. As a matter of fact, I can read how many charges there are. This is 0.51 picocoulomb, or 0.51 10 to the negative 12 coulombs, okay? If I want to know how much energy is stored, there's 0.19 times 10 to the negative 12 joules, okay? Usually the amount of energy in a capacitor is of the same order of magnitude of the charge, okay? So that is basically all of the information I have from this one in here. At some point, so let me bring the charge back to 0. Okay, so we have 0 voltage, 0 charge, 0 stored energy, and the capacitance should not change. I can measure what this one is because I know exactly it has no material between it, so it should be epsilon naught times this area. Make sure the area is in meters squared though, because right now it's in a millimeter squared. So I have to multiply this number by 10 to the negative 6 because there is a 10 to the negative 3 for every millimeter per meter. So when it's squared, it is 10 to the negative 6. Divided by 5 millimeter, which is 5 times 10 to the negative 3 still. So you have to be very careful with this conversion in here. But I can find this capacitance and compare it to this number. Okay. I need to check this, that this result matches with the theory. And then at some point, you're going to be dealing with a dielectric. This is basically where you introduce material. What they ask you to do again in here is that you have to have an area that is big enough, actually, around 200. Not so much. So that's good enough. I think that's too much also. That's good enough. So the area is 151, and then they ask you to lower this distance anywhere after 6.5 to like 7.5. So right now it's 7.1 millimeter. You need to bring the offset to 0. That means bring it all the way in. Right now it's all the way in, or bring it completely out. So it's back to epsilon naught right now. And let me bring this number, the dielectric constant, to 1. So right now the capacitance is no different than air, because this is assuming that I have air in there. That's the dielectric constant for the air. That's basically kappa. So kappa is 1. It's like vacuum. So this number does not change. But now if I change this number, look at the capacitance now. I'm putting stuff. What is the paper? Do you guys remember how much the paper was? Was it 2 point something? So
3.7.
Okay, 3.7. So if I put the paper, this is roughly how much capacitance now. This is without the paper. Okay, 0.24 and 3.7. Okay, 3.67. All the way to 5. So you're going to go on increments in here too, changing capacitance. And also, I need a voltmeter. Where is the voltmeter? I need to bring one also to measure these things. So right now I have 0 volt because the battery has no voltage in it. So again, if I change this thing in here, you see how much with a capacitor, how much voltage in here. It's this voltage actually. That's what you're reading at. So let me see the energy stored or the plate. I need the charge. Let's mean how many coulombs in here. Let's increase the dielectric and see how many coulombs in here. You see we're getting more and more for the same voltage now. Okay, so we're getting more and more for the same voltage now. Obviously, with paper, it's going to be around this number. Okay, but again, this is a small voltage. It's not even 1.5. It's not even 1 volt. This is barely more than 1 volt. Now you are almost 1 pico coulomb in there. Okay, so this is a small battery. This is what you go and buy from the store. This is the AA or AAA battery. That's exactly what that is. So if you're playing with this one in your home and have made that, and if you have access to a voltmeter to check the voltage, you could do that. You could actually play with this one in here. The only thing in here, how do you control that voltage with at home? It's going to be very hard. Once you connect it to this whole voltage that is connected, and actually you're going to feel it warm. So what you do in this case, you have to be very careful in here to probably have something in here to control the voltage. And one way of doing that is actually have a resistor in here that changes, okay? So, because that will consume some of that voltage that goes in here, but that is going to be actually building up the voltage in here. So we're going to talk about that one on chapter 26, actually, charging the capacitor. How do you actually charge it in lab? Because this is just in theory right now. It's still honestly not exactly how we would operate with it. So this is a voltage of 0 now, back to 0. So finally, there is this part in here. This is, you have a bunch of capacitors. At some point, you're going to be doing 3 capacitors in series. So you have capacitor C1, capacitor C2, capacitor C3. This one, you can leave it at 1. This one, they tell you to move it to 2. And this one to 2.5. This number. So how much equivalent capacitors in here? It should be 1 over C1 plus 1 over C2 plus 1 over C3, the whole thing to the power -1. Okay, so the total capacitance should be 0.531. So try it. 1 over 1 plus 1 over 2 plus 1 over 2.5, and the whole thing is inverted. Let's see here what my calculator says. Okay, 1 plus 1 over 2 plus 1 over 2.5. Remember, the answer has to be smaller than the smallest of them, which is 1. It's 0.526, according to my calculator. 0.526, whereas this thing is saying it's 0.53, okay? This thing has 3 sig figs. So this is off, actually, because if I go by the 3 sig figs, it's 0.526. So this is actually slightly over rounded up, okay? But then you're going to bring a voltmeter now and put it in here. At this point, there is 0 voltage because there is nothing on any of the capacitors. So let's make a voltage in here, 1.5, okay? Put it everywhere. So this capacitance has 0.316 volts. I'm going to read that, 0.316 volts. And I'm sorry, yeah, that's good. Then let's do this one in here. This one has 0.39 volt. So I'm going to add 0.39 volt. And this one should have more voltage, actually, than the other two because smaller capacitance. .789. When you add these numbers, it comes exactly to 1.5. So the voltages are not the same, but they add up to the sum of all of them, which is 1.5, okay? But the charges, did they give me the, no. They give me the stored charge. In this case, it's 0.79. 0.79 is in here, is in here, is in here. It's everywhere, 0.79. Coulombs in there, okay? So that should be the same charge in here. So if you're curious trying to find the stored energy, in this case is here. Stored energy should be the energy in all of them combined or that of the capacitor that is equivalent. Since I know how much charge, and since I know how much total capacitance, which is 0.526 actually, so according to my theory, it's going to be 1/2, which is 0.5, times the capacitance, which is this number, 0.526, times 10 to the negative 13. I'm going to ignore 10, just like what we did in class today when we were ignoring that micro business stuff. So I'm going to leave that for right now. So we're going to append it at the end. Times the voltage squared, and the voltage squared is 1.5 squared. Okay. According to this number, the energy is 0.5917. When I round this one, it's 0.592. Whereas in here, it's telling me it's 0.59. Okay. If I want to find the charge now, the charge, I know the entire voltage is 1.5 and the equivalent capacitance is 0.526. From this, we're going to find the charge, which is just the entire voltage divided by this capacitor. I mean, multiplied by this capacitance. What am I talking about? So again, it's the Q is equal to CV. So 0.526 times the voltage, which is 1.5. It's 0.789, exactly 10 to the negative 13. But in here, it's 0.79. Again, they are rounding up everywhere, okay? But don't go by that numbers, go by the sig figs in this case in here, okay? This is a known value. This is not 2 sig figs, this is a known value, okay? So this is the, if you want to find the overall voltage, for example, you bring this one in here and put it in here, and it's telling you 1.5 because it's a fixed value. But if you put it in here, for example, it's 1.024 volts, okay? So this device, it seems to have 4 sig figs in it, or at least up to this point, okay? But you go by the lowest sig figs in here, which is these numbers that have 3. But the point being, this is for the parallel, for the series circuit. Let's do the parallel one. Again, you're going to be doing 3 now. So we have the total capacitance, the total charge. Let's put this one back to 1.5, okay? Now, the capacitance in here is supposed to be twice as much. The capacitance in here is 2.5 times. 2.5, that is. Okay, so I have them all controlled. And now we want the voltage in here should be 1.5 across this capacitor. The voltage should be the same. This is 1.5. How about between this one and that one? It should be also 1.5. Notice if I move it somewhere else, it's giving me an exclamation point. Doesn't know what the voltage is. It's an open circuit, basically. So I have to really put it in the proper place. It's 1.5. It's the same as this voltage. As a matter of fact, the voltage in here too is 1.5. As far as this is concerned, the voltage you're looking at is the voltage between the battery, which is this voltage, and this one. It's the same voltage because this entire line in here is the same point. It has no resistance whatsoever. Same thing in here. This entire line is only 1 point. So what you were doing earlier, you were just measuring this values no more. Okay. Now the voltages are the same, but the charges are not. Because of the fact that now, before the charge was the same, in the previous example, it was the same. Now the charges are not. So the charges now are going to be, you can have more complicated stuff, 2 in series and 1 in parallel, or 2 in parallel and 1 in series. So you could have stuff that mimics a little bit some of the stuff that we did in the lab, and the class. But this thing is only for 3 in series and 3 in parallel in terms of the lab. So again, we're going to check the charge now. So if we want to calculate the charge, we have the voltage, we have the capacitance, so we should be able to find the charge in here. It should be equal to this voltage, which is 1.5 times this number. So it's going to be 1.5 times 10 to the negative 13 coulombs for this one. It's going to be 1.5 times 2, which is 3 times 10 to the negative 13 in here. So this is 3 as much charges than this one in here, okay? Because Q is equal to CV. And V is the same. C is changing now. Q, on the other hand, is equal to here and to 2.5 times 1.5, and that is what? 2.5 times 1.5. 3.75 in here. So there is 3.75 plus 3, that's 6.75, plus 1, that's 7.75. That's how much charge is drained in here, okay? Why did I get in here? Oh, did I make a mistake? It's 1.5 in here. I'm sorry, 1.5 times 1, that's 1.5. Plus 3, that's 3.5. That's correct. Plus 3.75. So it's 8.275, 8.25, okay? So this number is correct. The charge, the total charge that you removed from the battery. And the energy, you could do the same thing now. You could find that the equivalent capacitance is very easy in this case. It's 1 plus 2 plus 2.5, which is 5.5. Okay, so this is a match. The energy now is that 5.5 divided by 2 times the voltage squared. So again, 5.5 times the voltage squared, which is 1.5 squared. The whole thing is divided by 2. It's 6.1875, okay? Again, they're rounding up to 6.19, which is probably good in this case because of the sig figs. There are three sig figs, so this is also a match. Okay, so this is basically in a nutshell what the lab is. So this is what they are asking us to do. Let me stop sharing the screen and go back into my PDF to follow the questions and things like that. No, that's not it. Where is lab 2? So again, I just went to the simulation and we went through everything in here. So they tell you to put it at 400 millimeters squared and 5 millimeter separation and calculate C naught. So now you have epsilon naught, which is given previously. You have A, which is 400. You have D, you're going to calculate the number, just like I did in my calculator. You're going to do that, okay? Please make it in full sentences and don't forget units, okay? So again, you're going to separate the value in here. So now we're going to look at the separation, which is 5 millimeter, but they want it in meters, so you can write it. What is it? 5 times 10 to the power
-3.
Thank you very much, okay? And here the area is going to be 400 meters squared, which is 400 times 10 to the -6, or 4 times 10 to the -4, okay? Meters squared. And C naught is whatever you end up with, okay? Something times 10 to the -12 something, or 10 to the -13 something, okay? So that's going to be the number that you're going to be reporting in here. Then you come to this table. For this table, remember the voltage, you can increment it slightly from the battery. It's sitting at 0, and it goes all the way to 1.5 volt. So try to have it in increments more or less of 0.15, okay? If you do that, you're going to go from 0 to 1.5 accordingly, okay? But don't worry about it if it's slightly more or slightly less, it doesn't matter, as long as you have 10 values in here, okay? For that. You're going to look at the charge. So you need to pull that charge thing to read how much charge. Do not put a calculated value in here. This is based on the observation. This is what you see from the device, okay? The storage energy, again, you're going to put it by itself. The device will let you do that, okay? Now, how do I find the electric field? Since I know the voltage from here, from this part, from what the voltmeter is giving me, all I have to do is divide it by this distance here, D. That should be your electric field, okay? So the electric field is a calculated value. The electric field is this voltage that the voltmeter is giving you, and you divide it by that D, this distance, separation between the two plates. And now, remember, this is the first step where there is only one capacitor where you made the area 400 and separation is already 5 millimeter. You're going to take this value and square it, put it in here. You're going to take this value and square it and put it in here. And if you like, ignore or at least state in the lab report that you're not including in the table 10 to the negative 12 so that you'll have manageable numbers, okay? Because you're going to have 10 to the negative 24 in here. Same thing. No, this is voltage, so that's fine. But the energy is going to have that many things, okay? But in the answer, you need to restore back the units, okay? You need to restore back the scale. So the electric field, you measure this in here, all you have to do is square it now. And the energy density, which is this value, divided by the product of these two numbers in meters. Again, you can opt out of the big scale unit 10 to the negative whatever and say that, hey, I'm just factoring this out in your answer. Okay, somewhere you have to tell me that, because it's going to be too long in here to write everything with 10 to the negative, but you need all of this data, and that's why it's worth a lot of points. 1, 2, 3, 4, 5, 6, 7, 8, and then you have 10, so 80 points in there. Everybody knows what you're supposed to do in this case?
Professor, could you repeat the energy density, please?
The energy density, since you already have the energy from this step, from the simulation. Let me go back to the simulation to find the energy for this part, okay? Stop sharing.
Never mind, I see. We do the energy that we get and we divide it by the area and the distance.
Yes, that should be the volume, okay?
Yeah, I didn't see that.
Okay, so in here I have the energy. So let's go back. Let's say, for example, I'm at this point in here, 0.625, okay? So the energy, according to this device, is 0.14, 10 to the negative 12. Divide that by the volume, which is this number times this number. But don't forget the units, okay? So divide that by the volume, and now you have the energy density, U, okay? If you're looking for the electric field in here, only thing it shows you is the electric field lines and the charges, but that's not good enough. You need the number. So for the number, it's this voltage divided by this distance. So you'll need that. There is nothing in here for some reason they removed it. It used to, what is that? Field detector so that you can measure the electric field. So they removed that, okay? So now you're gonna calculate that. So you have to do some honest work there. Does this table make sense to everybody?
Yes.
Okay, very good, thank you. Now we move to these questions, of graphing things. You already have U and V squared. If you look back on the table, you will see that you have U here and you have V squared. So you have a bunch of data in here for the energy and the voltage. This is your independent variable. This is the one that changes because this is the one that you control yourself as you're changing. I mean, you changed V, but V squared also changes based on your own wishes. The energy is your dependent variable. This is your Y axis. This is your X axis when you're graphing. So the X axis is here. The Y axis is here. Now, if you look at this graph, again, this is going to be V squared, and this is going to be the energy U. So you have to have them properly labeled. So if you're going to print this one and do it by hand, that's fine. Or if you're going to use Excel for it, that's fine. You need to have the axes properly labeled, and you have to have the 10 points, all of them represented on this graph, okay? And you have to have, so use Excel to plot. So it's telling you to use Excel to plot V squared, and you using V squared in the most left column in Excel and attach it to it. So you're going to attach that. Since we know that U is equal to 1/2 of C naught V squared, it's a line actually, it should be a line. Determine C naught using the slope. So if you find the slope of that function using either the slope function from Excel or using the fitting, which is the trend line, and taking the slope off of it for the y-axis, a function of x-axis, that value is 1/2 of C naught. All you have to do is multiply it by 2, and that should be your C naught. Okay? So now you have another way of finding C naught from the data. You're going to compare it to what you have measured. Remember, you have measured it a long, long time ago using the formula for it. You measured it in here, in this question 3. So you're going to compare it to C3, the question 3, I'm sorry, that you found. So you have a different way of finding it, comparing it, and tell me if it matches or if there's an issue with it, and tell how you can address that problem. Same thing. You have U now as a function of Q squared. So if you go back to the table now, It's the same table. You have Q squared on one side, and you have the energy. So this is your x-axis, this is your y-axis, and now you do the same thing. Except now you have a different thing. So now this will be your Q squared, and this is your energy, and you're going to plot it, and it should be a line. Don't forget to label your axes and make sure you put all of the 10 numbers in here in this graph. And then you're going to use the equation to find C naught, because 1/2 C naught is actually the slope. So C naught is 1/2 the slope. So whatever the slope in here multiplied by 2 and invert it. That's going to be your C naught. Okay. Then use the percentage. So again, we're going to refer back to use the result from 6 to compare these values. So you not calculate the percentage errors. So as in question 5, calculate the percentage error. This is a percentage error basically. So use the value that you calculated from question 3 and the one that you just measured using this dependency, and you're going to find another comparison now. And you're going to tell me, is the error acceptable or not acceptable, or too high, too low, and what went wrong, okay? Now, also, we need to make a graph of u, little u, that is the energy density, as a function of E squared now. So again, now your x-axis have changed. So the electric field is going to be your independent variable. Why am I doing this? Why can't I do it faster? Okay, so the electric field now is here. The electric field squared is here. This is your x-axis, and this is your y-axis. Okay, so for this part, this will be your y-axis, and this will be your x-axis. So you're determining the energy density as a function of the energy, of the function of the electric field squared, I'm sorry. So now you come back to this graph now. Your x-axis is E squared, and your y-axis is little u, the energy density. And again, you're using this expression now. The slope must be epsilon naught over 2. So if you compare the slope, is it epsilon naught over 2? It's epsilon naught over 2, basically. You're going to calculate epsilon naught and compare it to the known value. Similar to what we did in the previous errors. So is epsilon naught acceptable or not, okay? This is the dielectric. This is the second tab in that same graph. So basically now you're going to have anywhere between 195 to 205 the area. So you have to adjust the area so that it matches this number. And the D to be anywhere between 7.5 to 8.5 millimeter. I think I took 7.1. You can take any number in between. So again, it's your choosing. Please do not choose the numbers I chose. Make sure you stick to these values though. And the maximum, yank the battery all the way to 1.5, okay, volt. Put it up in there. And the constant, the dielectric constant, remember it varies from 1 to 5. You're going to put it back to 1, as if it's air or vacuum. And the offset to where? And the offset to 0. That means it's fully inside, okay? That means you pushed it. Right now, the offset is 17.9. So when you push it in, it's already to 0. So make sure it's all the way in. Okay. Now calculate the capacitance. So now the capacitance, when epsilon r is 1, which is like vacuum or air, then it's just the old capacitance, except now you have your own area and your own D. So this number is not the same as the previous one. So this is a new C naught. So it depends on you. So now, if you don't tell me in this question what you chose for the area and what you chose for the distance in here, I wouldn't know if your calculation is correct or not. So this question, you must include the data that you chose for it. Okay, make sense?
Yes, it does.
Okay, very good. Thank you very much. And then stick with this configuration. If you make any changes, if you hit the reset button, for example, you're going to lose this configuration. So you need to come back to it. So that's why it's very, very important to put those numbers next to you somewhere safe, okay? Because once you choose an area between 195 to 205 and a separation between 7.5 to 8.5 millimeter, those numbers stick with you for the rest of this part, because you're going to rely on those calculations for C naught to compare it. Otherwise, you're going to get big errors. And I will tell you that probably most likely that's what happened. Somehow you changed these numbers and now you have, that's why it's completely nonsense, okay? Again, now start changing your kappa by increments of 1.5. Remember, kappa changes from 1 to all the way to 5. So now you're going to change it and pull the capacitance, and you're going to see how it changes. So it's going to give you one value, second value, third value, so on and so forth. So C is changing now. Okay. We need to make a graph for C as a function of kappa. So we know how C depends on kappa. It's just a linear function. Here it is. So if I plot C as a function of kappa, it should be a line, the slope of which should be that epsilon naught that you calculated, C naught that you calculated. Your own C naught, not somebody else, okay? That is actually the slope, okay? So again, if you work together with somebody else and you happen to choose the same numbers, that's fine. Please make sure you include his or her name in the report there too. So we are here. So calculate now, that part is done. So we're gonna graph now kappa, which is a number that has no dimensions. This is a good place to remember this thing has no units, but C definitely has units, okay? Again, you can use Excel and include the Excel file. You're gonna be graded on that. So this is the equation you're supposed to graph. Did you get the same value of C naught or not? And I'm sorry, you can find now the experimental value of C naught you get from here, and you compare it to the measure calculated one, and you tell me how good it is. This is the last part, part C of the lab, where you actually come to the multiple the configurations. And that's the first thing you're going to do 3 in series. And the total capacitance, you're going to show that. You're going to show the total, what is it? The stored energy also, we need that. And we need also the voltmeter, okay? We need also the voltmeter. So if we continue with this one, now you're going to measure the total voltage. V max is from top to bottom. This is 1.5. It should be 1.5 volt, okay? And then you're going to measure V1, the voltage across these capacitors. Make sure in here to choose the capacitance as I tell you. 0.1 picofarad or 1 times 10 to the negative 13. 0.2 picofarad or 2 times 10 to the negative 13, and 0.25 or 2.5, 10 to the negative 13, and that is basically the numbers. Make sure that these capacitance are set correctly, okay? And then calculate V1, measure V1, I'm sorry, measure V2, and measure V3 in volts, okay? And if you add this 3, it should add up exactly to 1.5 volts, okay? Now, using the given values of the capacitance, find the charges. Now, we know what the voltage is. And we know what the capacitance is. All I have to do is multiply this one, this voltage, the voltmeter that gave me, times the capacitance of this capacitor, and plug in the number in here. Do the same thing in here, and do the same thing in there. What is the total capacitance in farad? So the total capacitance in farad is actually given by this device. This one, the total capacitance, okay? Read the meter. Use the formula to find the total capacitance. So basically 1 over, I already did that. 1 over this C plus 1 over this C plus 1 over this C, and invert it. Do the two numbers match, okay? And compare the values. If there is a discrepancy, you need to probably discuss it. And there is a discrepancy already, okay? As I found out earlier. When you include the sig figs into account. Now, that was not actually the last one. This was the last one, okay? This is the parallel plates capacitor. Again, you're doing the same thing, except you have 3 in parallel now. Again, you're gonna find the overall voltage, and you're gonna find V1 and V2 and V3, and they should all be the same as I did earlier. So they should be the same voltage everywhere. And they are actually, because it's a parallel configuration, they should be, okay? So that's part of your answer. Q1, I calculated Q1 because we have C1 and you have V1. So all you have to do is just multiply the two and you're in business, Q2 and Q3. And what is the total capacitance in farad? Read the meter. Again, read this capacitance in here and compare it to the total capacitance when you add them. You add this one plus that one. It should be the total capacitance, okay? And compare the two values and the conclusion. Straightforward, isn't it?
Yeah, it's just like busy work.
Absolutely, that's the intent of it. That is exactly what it's supposed to be. Okay? You're going to earn that unit of this class for the lab part of it, okay? Any questions for me?
I don't have any.
Not really. Like Marcella said, it's just going to be tedious. Everything really makes sense. Everything was explained pretty clearly.
Very good. So I'm going to stop the recording right now. And then if you choose to stay, that's fine. If you choose to work on it later on, that's fine. If you have difficulty with it now, just shout out, because I'm going to turn off my mute my microphone and also turn off the video. So if you choose to come back later on and ask me questions about it, that's fine, but you should not have any difficulty with this lab. Okay?
Okay, Professor.
Thank you.
Stopping the recording now.